Let me just share my screen. Doo, doo, doo. One second. Hello, good evening or good afternoon for you probably. I'm Elmar, and today I'm presenting about maximum power point tracking of solar arrays. So I'm Elmar. Like I participated in a solar car race myself. I make maximum power point trackers, impacts their car. I'll be modeling some solar arrays and explain how maximum power point tracking works in a solar array. I'm explaining some examples with diodes.
Doing well.
Sorry, I couldn't hear you. Well, I'll go on. I'll explain some examples of how you can use diodes to get more solar out of your array when you got shade. I'll explain something about efficiency of maximum power point trackers, and then some special tricks that you can do with maximum power point trackers. For example, putting them in series or doing decentralized maximum power point tracking. Examples of solar cars. This is a solar car. And as you can see, there's like a canopy for the driver in the middle. And then that generates shade on the array. And later on, we'll see that the cells that get shade output less current. And if you group them together with other cells, that makes provide some challenges for maximum power point tracking. Well, like here's another car with shade. This is why the shade is created. Like the sun comes on the array under an angle. There's like an object, for example, the driver canopy, in between the sun and the solar array, and therefore you have shade. Also, like different solar cells on the car are pointed towards the sun on different angles. Therefore, the amount of irradiation on different solar cells is different. And then if you group them together in a group, that makes it difficult to track the maximum power point of both cells that have different angles. Simple solutions for that. You can just make sure that you have like no shade on your array at all. Like for example, how those guys did it, but usually that has some negative impact on your aerodynamics. You have this like other example of Michigan. They made a car and they just put all the solar cells on the back and nothing next to the canopy. So you don't have shade. That's all great for the array, but it does make your solar car a little bit bigger, which is then not as good for your aerodynamics. This is a picture of Solar Team 20. The reason I put this in there is that what they did is they made the area, and they put, first of all, they put the canopy on like one side of the solar car, so you only have like shade either in the morning or the evening and not both. Something else that smart they did is like they put like big solar cells everywhere on the car, but they choose to like cut the cells that are next to the canopy, so you have like a little bit smaller groups next to the canopy. Therefore, it's easier to deal with the shadow effect of the canopy because you have smaller solar cell groups. Let's see, this is the same car. Solar cell modeling. So how would you model a solar cell? Usually a solar cell is modeled as a current source, and the magnitude of the current is usually proportional to the amount of sun on the solar cell. Then there's usually a diode modeled like in parallel with the current source. Usually with silicium solar cells, it's around like 0.6 or 0.7 volt. And there's some series resistance. Let's see. So using this model, you can track an IV curve out of your solar cell. So this is a picture out of a data sheet of a SunPower solar cell. And what you see on the x-axis is the voltage of the solar cell. And on the y-axis, the current. And as you can see, as you vary the voltage, the current is varied. So if you put a voltage of 0 volt on your solar cell, you get the maximum current. It's usually called the short circuit current. If you don't pull any current at all, it's like all the way on the right of the graph, you get the maximum voltage. It's usually called the open circuit voltage. But the power you get out of the cell is the product of current and voltage. So like if you would take like 1 point on the graph, you can make like a little square underneath it. And the area of that square is the amount of power. And usually the maximum power point is around 0. If the open circuit voltage is like around 0.7 volt, usually the maximum power point is like around 0.6 volt, like where it's usually like, well, like at the maximum power point voltage and the maximum power point current. Well, yeah, most important is that as you get less irradiance, the maximum current decreases and the voltage stays approximately constant. Like there's some temperature dependence on the maximum power point voltage, but that's relatively small compared to the current dependence on irradiance. What do we see here? This is a little animation. And what you see here is the irradiance of the cell increases, and then therefore the current increases, now the irradiance decreases, and then the maximum power point current decreases. And that little dot that's on the blue graph represents the maximum power point current, and then the little red dot on the orange graph has the power on the y and on the y-axis. On the x-axis, it's the voltage of the cell. And like this is a typical algorithm, like tries to keep the maximum power, like which is the orange graph, as high as possible. And how I was doing that is that it's setting like little steps left and right, like it decreases and increases the voltage a little bit. And then like by stepping to the left, it sees if the power increases or decreases. If the power increases, it keeps going left. If the power decreases, it will change direction. So like it will always search for the top of the power. Let's see, what else? So this picture we've seen before. So here we have two solar arrays that have a different angle. Therefore, some solar cells get more irradiance than others. Like, for example, the ones that are pointed to the sun might get 800 watt per square meter. The ones that are not perpendicular to the sun might only get like 500 watt per square meter. And what I did here, I made some maximum power graphs and voltage graphs. And what you can see here is that, the solar array that gets less irradiance has a lower maximum power point current, and its maximum power point therefore is also at a lower current. And now, if we put those two solar cells in series with each other, or like one solar cell is actually multiple, what we then see is that we add up the voltages, and the current graph stays the same. So like the next slide is, let's see. On the next slide, I added the voltages of the two graphs. And then we got a new graph. And on the right, I drew the maximum power point, the maximum power versus current for that new IV curve graph that we get for this series combination. And what you can see here is that there's two little peaks on the mountain, of which one is higher than the other. Both of those peaks are local maximum power points, and the highest one is the global maximum power point. And lots of maximum power point trackers only do local maximum power point tracking, and therefore they can get stuck on the wrong peak, and then they'll keep optimizing to find like the maximum power point around that peak, but they might not always be aware that there's like a way higher peak elsewhere in the graph. So that's something you should that you should take into account when selecting and testing a maximum power point tracking. Like you should always look for a way so you should always see if it has a way to actually find the global maximum power point. Let's see. So here's like an example of a maximum power point tracker. And the red and the blue dot again is like, or let's see. The blue and the red dot is where it's actually tracking. And the orange and the green dot is where the actual maximum power point is. And you can see that it's not always tracking it correctly. Not super clear from maybe, but like sometimes you just get stuck at the wrong peak. Like ideally, if it would always work perfectly, like the blue and the green dot would always be at the same spot, and the orange and the red dot would always be at the same spot. But in practice, that's not always the case, as it's like trying to look for it and not always sure where to look. What else? This was like an example of like Delft like racing in Africa, and they like they had this one race day where they got like a lot of shade on the array, and their tracking algorithm like completely got out of control, and they had like almost zero income, like because they all left all those trees on the side of the road and they made shade, and then the maximum power points got confused. I'm not gonna play it because it takes too long. Or maybe now I am playing it. Let's see. What else? Diodes. Why do we do diodes? Let's see. So if one, like I said in this top picture, there's like 3 arrays in series. One of them has shade. So the maximum power point current of that one array in the middle is lower, it might be like 1 or 2 amps, whereas the current maximum power point current of the other 2 arrays might be like 6 amps. Well, normally if you would not have that diode, you would only be able to pull like 1 or 2 amps out of all the arrays, like reducing your maximum power by like a factor of 3. Now what you can do with this diode is like bypassing the solar array. So this bad array, you're like, okay, your current is too limiting. So what we're gonna do is we're gonna just route the current past you. Also make sure that like the voltage of that shaded array becomes like close to 0 volt or even a little bit negative because of the diode drop. So like that middle solar array, even though it still has some power, you don't utilize it, but because you can use that diode to bypass the current, you're still managing to get the maximum power point of the other two solar arrays that are performing well. The bottom picture, that's also important. If you don't place diodes, and you do have shade on one of the arrays, and you still are trying to draw the high current that you could get from the non-shaded arrays, could cause a negative voltage across the shaded array. Therefore, you would actually dissipate extra power in that shaded array rather than extracting power from it. So what's happening here is that actually you're by not having this diode and pulling a high current, you're actually transferring some of the power of the non-shaded arrays to the shaded array, and therefore it might get super hot. And well, in this picture it even catches fire. I've never seen that with a solar car, but I have seen teams that did not put diodes in their array, and therefore solar cells did get damaged because they had to dissipate a lot of power while they were shaded. Not good. Another picture, how do you place your diodes? The top picture shows it like a diode per solar cell. But as the voltage of a solar cell is usually only 0.6 volt, and the voltage drop over a normal diodes when it's conducting could also be close to 0.6 volt. Let me repeat. When a diode goes in conduction, rather than having plus 0.6 volt of a solar cell, you'll get minus 0.6 volts for the diode drop. So actually, you get some loss from the diode, which is not ideal. So sometimes it's better to bypass multiple solar cells all at once in order to mitigate some of the diode drop when using normal diodes. There's also other, there's a lot of different ways to connect diodes. It's just important to know that when a diode isn't conducting, it has a negative voltage drop. So the more diodes that are conducting, the more negative voltage drop you get. So if you can bypass multiple solar cells at once, that is sometimes better. That being said, nowadays you can buy smart bypass diodes, which is basically a diode with a little switch in parallel. And they can cause the diode drop voltage to go to close to 0. And in that case, it would be good to go for the top string again, just give every cell a diode. Let's see. There's lots of ways to optimize your diode connections. I'm not gonna go into it in depth because it's only relevant if you're using non-ideal diodes, and nowadays you can buy smart diodes, which is something that got pioneered in 2006, I believe, by a little small company called OKE Services in the Netherlands. Nowadays, there's big companies like Texas Instruments that sell an all-in-one, pretty much package that looks like a normal diode, but internally it has some small stuff. Internally it is a normal diode, but in parallel with that is a MOSFET switch. And there's a controller that switches on the MOSFET when the diode is conducting, and therefore it makes sure that the voltage drop across the diode is close to 0 volt. One thing you should be aware of with those things is that they might confuse MPPTs. With MPPTs I sell, I managed to make them compatible with the smart diodes. But it's always good to ask your maximum power point supplier if their algorithm is compatible with smart bypass diodes. the reason for that is that as the diodes have this smart switch, let me export what's the difficulty again. Yes, the switch turns on when the diode is in conduction, but it takes a little time to turn off once the bypass current drop to 0 again. And therefore, when you're increasing the voltage on, like, let me just rephrase this. Do I have a slide on this? No. Like, they stay on for like a couple of milliseconds, like longer than they're supposed to, once the bypass current drops to 0 again. So when you're tracking an IV curve, and you're decreasing your voltage, therefore like making sure diodes start turning on, like you're able to track your IV curve correctly. But as you are increasing your voltage again with your maximum power point and track an IV curve, you get a slightly wrong IV curve as the diodes stay on for a little bit too long. So when your MPPT is tracking IV curve, it should be doing that by decreasing the voltage and then tracking an entire curve, and then based on that curve select the maximum power point, rather than tracking an IV curve while increasing the voltage, because when you increase the voltage, it makes that bypass diode turn off again, and then that takes a little bit too long with smart bypass diodes. Therefore, your graph gets a little bit distorted. But like, if you want to know more details on this, you can just ask me in private sometimes, because it's a quite long topic. MPPT efficiency, the next thing I wanted to talk about. MPPT.
Just make sure we're muted.
Is there a question? I cannot hear you. I'll go on. Efficiency. Yes, this is a graph of an MPPT efficiency. And it plots the efficiency for different input voltages. Whereas the battery voltage is the same. And as you can see, the efficiency is higher when the input voltage is higher. Like, basically, like, the MPPT is a boost converter. There's an input voltage and output voltage. And as the input voltage is higher, it's like as you connect more solar cells, the efficiency gets higher as well. So with regards to MPPT conversion efficiency, you want to like make your like solar array groups as big as possible. But that's again worse for your tracking efficiency, because then you're combining multiple cells that might have different irradiances. So there's like a little bit of a trade-off here. The efficiency. This is another graph where, rather than efficiency, I'm plotting the power loss for different input voltages. And as you can pretty much see that the power loss is pretty like independent on like actually how many solar cells you connect to the input. So therefore, but like as you have connect less, like if you connect more MPPTs, more solar cells to the input, your total power gets higher, and therefore, because the efficiency, like is one minus power loss divided by total power, like that number increases as the total power increases. What else? Series MPPTs. Yeah. So like I've seen some teams, also like American teams, using these boost MPPTs that connect with their output in series. Let's see, do I have a slide on that? Here, yes. So let's see. Rather than like, so the picture on the left is like a couple of solar cells connected in series to like a big boost MPPT. What I've seen some teams doing is like buying those little red Nomura MPPTs. And what they do is they, rather than putting the solar cells in series, they connect all the like little solar cell strings to an MPPT, and then they put the output of the MPPTs in series. And it's claimed that hereby you can do better maximum power point tracking of like individual smaller cell groups. But let's see. I've had a lot of teams that have had negative experiences with this because because this only works well when the variation between the power of the input groups has small variations. Like all the marketing materials and datasheet of the Nomura MPPT show like examples and calculations where there's only like a 10 or 20% difference between the cells. But then once the differences get bigger, it's not able to track the maximum power points anymore. Let's see. I can do like a little like example calculation on this to make that clearer. Let's see. I need a Jamboard for that. Jamboard. No, Jamboard. Jamboard. This is not. Sorry for the new Jamboard. Can everybody see the Jamboard? I'm assuming yes.
Yeah, we can see it.
Let's see. So what I wanted to say is, let's say you have two solar cells. And you connect two MPPTs in series. So this is an MPPT. And then on the right side is the output of the MPPT, on the left side it's the input. That little thing on the left, what I drew is like a solar cell. And now I connect like a battery here. I just model it as a constant voltage. And let's say, just give a simple example. Let's say the battery is 60 volts. Like usually, like you would have like a higher voltage battery and you would connect more than two MPPTs in series, but that's overcomplicating it a little bit for now. So let's keep it low. So now, like in the ideal scenario where both solar cells are the same, they output the same output current. Let's see, and let's see. Let me just draw a little bit. Let's say you have 20 volt, 3 amp on the input. This is like maximum voltage, maximum power point voltage, maximum power point current. And then the top one is also maximum power point voltage of 20 volt and a maximum power point current of 3 amps. So this makes 60 watt on the input for both of them. Because they both have equal input power, they also have equal output power. And because of that, they have an equal output voltage. And because they're placed in series, they have an equal output current. Okay, this is like a balanced system where the input powers of the MPPTs are the same, and therefore the output powers of the MPPTs are the same. Let's see. But now, what happens if let's say one of the arrays gets shade and therefore the maximum power point current decreases, and therefore the input power of this MPPT becomes 20 watts. And now our example doesn't really work anymore. So let's see. Now the total input power is 20 watts for this array, 60 watts for that array. So the total of that is, if you add them up, you get, see, you get 80 watts on the input. You know your battery voltage is 60 volt. So ideally, if everything would work well, your current here would become your total power, like assuming like everything is 100% efficient. The current here would become 80 divided by 60 volts, where 60 volts is the output voltage, 80 watts is the input power of all arrays combined. Watt divided by 60 volt is, then you get 80 divided by 60 is 1.33 amps. Now you know the output current of each MPPT as well, because they're all placed in series, so they're all 1.33. Now the output voltage of this top MPPT becomes 20 watts divided by 1.33. If everything would work well and would be on its optimum. 20 divided by 1.33 is 15 volts. Now the bottom one, you get an input power of 60 watts. So the output power also becomes 60 watt if it's approximately 100% efficient. And then because you already know the output current 1.33, now the voltage there becomes 60 divided by 1.33 is 45 volts. So this is like ideally what would happen, like if you put MPPTs in series and one of the arrays is shaded, it would just like change the output voltage. Like the output voltage ratio basically becomes the same as the input power ratio. But now, because a lot of teams do this trick while using boost MPPTs, they like it does not work, because this top MPPT has like a maximum power point of 20 volts, and like if the system works properly, the output voltage should become 15 volt, but it cannot do that because then you would need a buck MPPT and not a boost MPPT, because for boost MPPTs the output voltage always needs to be higher than the input voltage. So like, and also like you see that the voltage of the bottom one should become 45 volts, but usually like the voltage rating of the MPPT is rated at something lower than 45, like maybe like 35 or something, and that therefore can also not do that. So like in reality, like putting MPPTs in series is nice, but it does not work with boost MPPTs with limited ratings. Like, let's see, what else did I want to show? There's a paper Tokai did on this. Let's see. It's called like and they figured out that this was a problem. And then what they did, they make buck boost MPPTs. So you could just vote, make sure the output of the MPPT is lower or higher than the input. And like they spent a couple of years on it, and like finally they were able to figure it out. This is the MPPT they made. Like it's a nice green board. Like efficiency is like not like around like 98.5% peak, which I think is not very high for solar car, but what they do is they make beautiful buck boost MPPTs and they put them all in series. And they managed to make it work with a lot of research and a lot of puzzling and a lot of data acquisition and a lot of good design. Yeah, but as you can see, they have like this data over their like over like some of the race days, and as you can see, the boost ratio varies between values that are less than 1 to values that are more than 1. So if you would just have like boost MPPTs, your boost ratio could only be higher than 1. And then as you can see, like as you get shade on your array, like your system stops working efficiently. Like well, here it does work because they have buck boost, but it would not work very well after 4 o'clock in the afternoon if you only have boost MPPTs and you put them in series. But yeah, like it's a little bit complicated. But like the summary is like don't try to don't expect series boost MPPTs like the Nomura ones to fix your shading issues. Like it might actually make it a little bit worse. In theory, it should work well for changing small differences. I think someone's putting something in the chat. Let me have a look. That is the best explanation of a possible issue with series connected boost MPPTs. Yes, thank you, Alan. And Alan also said, I believe it's also possible for smart bypass diodes to confuse IV curve tracers. Well, like it would give you a little bit of a different IV curve. Like, well, you can trace IV curves like in 2 different ways, right? You can start with the maximum voltage and then go down to 0 volts. Or you can start at 0 volts and then go up to the maximum voltage of your solar array. And with smart bypass diodes, you will see that depending on what direction you're going, you get a different curve. And the reason for that is that the diodes take a little bit of time to turn off. Yeah. Let's see. Output series MPPTs. I do have like suggestions for systems that do work. But I first wanted to like show what does not work, because I feel like a lot of teams are getting confused with these MPPTs. They use them, they don't have telemetry, so they don't measure what's actually going on. Then they get like less power than they're expecting, then they're disappointed. Yeah, it's just a little bit sad that like if you are doing series MPPTs, you need data acquisition on every MPPT, and you need to think a little bit better about what's actually going to happen when you have shades. Like, well, yeah. What else? Works well for solving small differences, does not work well for compensating shaded arrays. Yeah, and that's the thing you want to solve, right? Because the shade is like what's making things bad. Please read the Tokai paper like in more detail. What else? Yeah, so in 2015, I made like a little system for Solar Team Twente called Sabine. What does it stand for? Solar Array Balancing Interface, new edition. Basically what we did, let's see, maybe like some of the people in here know how to make like battery management systems, like because like really like a solar array is just like a series string of little voltage sources. Like a battery is also like a little string of voltage sources, like they're called batteries instead of solar cells. And like the first step, like in making a system like this, is actually just connecting voltage monitors to your solar array. Like you can just use the same like voltage monitors that you can use in batteries. Well, the ones that you use for your batteries are usually optimized for measuring voltages around 3.7 volt. So what you do is you put 6 solar cells in series, and then you call that like one, and then you don't do it per solar cell, right? You still make groups but you make them a little bit smaller, and like then you're able to like measure the voltage of like every 6 solar cells that are placed in series. And then what you will see once you start monitoring that is that all those voltages are like a little bit different because they're all placed in series and they all get a little bit different irradiance. And then once you start noticing those differences, you can see which cells are weak and which cells are strong. And what you're trying to do is to transfer some energy from the strong cells to the weak cells so they all become equal. That's like the short summary of what a system like this is doing. We ended up putting like 100 converters on the array or something like that. And all they were doing is like transferring energy from strong cells to weaker cells to make them all equal. Let's see. There's also like literature available on this. You have to search for DMPPT, like decentralized maximum power point tracking. And usually like decentralized maximum power point tracking systems are systems that connect in parallel with your solar array. So like if you would deactivate the system or turn it off or disconnect it, you would just be back to your normal system. But then when you turn it on, or once you connect it, you start balancing the cells. There's lots of different ways to do it. Let me just think for a bit. Yeah, so I was on AliExpress the other day, like, and they had like active battery balancers, and like they like it's amazing like how simple of a trick they did. They have like inductive battery balancers and like capacitive battery balancers. But the same principle that they use can be used on solar arrays, and because it's so simple, I can explain it. Let's see. Let's go back to the Jamboard. Where I lost my computer. I think. Oh wait, it was here. Like I wish we could just be in a classroom or something with a whiteboard. Like, let's see. But it's kind of like that, right? Let's see. So let's see. Inductive solar array balancer. So we have 2 solar arrays in series again. I'm just gonna do 2 because it's too late for me to do anything more than 2 right now. Let's see. Let's just start with the problem. This one is 1 amp, 20 volts. This one is 3 amp. Is that a good example? Yeah, probably 3 amp, 20 volts. This is maximum power point current, maximum power point voltage. What would normally happen is that you would connect your maximum power point here. And what would normally happen, like, well, you would either like draw the 3 amp and like bypass this, and then you would just only get like the 60 watts from the bottom array because the other one is shorted, or which is 60 watts. So scenario 1 was you short top one with your bypass diode and you get like 60 watts from your bottom one. Scenario 2 is, so this is if you run it like 3 amp, right? Scenario 2 is you run the thing at 1 amp. Well, what happens at 1 amp? Well, then like this, like you don't get your 3 amp out of this bottom one, but you get 1 amp out of your bottom one. And maybe like this, the voltage increases to like 21 or 22 volt, but like it's not super significant. So now your total power becomes like, let's say it doesn't. Now your total power becomes 1 times 20 times plus 1 times 20. It's like it's even worse, like it's 40 watts. This is if you run at 1 amp, right? But like ideally, you would get the 20 watt from the bottom. Right, this is 3 amp. Ideally, you would get the, and then this is wrong as well. Ideally, you would get the 60 watt from your bottom cell, and you would get the like the 20 watts from your so ideally scenario 3, you get 60 watt of the bottom cell and 20 watt of the top cell, and then you get like 80 watts. So then so scenario 1 is with a diode. Scenario 2 is like no diode, because we just run it. Scenario 3 is balanced, but it's a, like, how do we call it again? MPPT. It's like the thing they use in research. But then what you have to do is fix the issue of this difference in current. So what you want to do is you kind of like want to steal. You want to steal 1 amp from the bottom one. And then you want to put that 1 amp back on the top one. So, well, let's see. Because the voltage is the same. Like you take 1 amp here at 20 volts, so you subtract 20 watts here, and here you like add 20 watts to the top one. So basically, you have some kind of like transformer that like takes 20 watt from the bottom and like puts it back on the top, and then instead of 1 amp on the top, you get like 2 amp there. And instead of 3 amp on the bottom, you get like 2 amp there. And then 2 amp times 20 is 40 watt, 2 times 20 is 40 watt, and then together they'll get 80 watt. And then the MPPT just runs at 2 amp. But it gets 2 amp 40 volts. Whereas earlier that 3 amp had only 20 volts. Or that 1 amp at 40 volts. So this is what you want to do. The way you can do that is inductive or capacitive. Let's first do inductive. So that's like with those things that you go buy on AliExpress. Like I just got this from AliExpress, like, but you can probably buy it somewhere proper as well. They just have, they're like 2 cells. They have like a little inductor and a switch and a diode. Like how is this connected? It's like this. We have an inductor there and then a switch here. Let me just see, we're at 1 amp 20 volt, 2 amp 20 volt. But the important thing is that we steal 1 amp here and then we put it back there. So kind of like we have like we steal 2 amp in total from this node, and we put 1 amp back here, and we take, let's see, how do I draw this? Yeah, we have the 1 amp here as well. So what we do is, how much time do we have left? Not much, right? Well, basically it's making it like this. Like these are average currents. Let's see. So what it's doing, like it's the switches are on like 50% of the time, each of them. Like, and once the one is on, the other one is off, and once the other one is on, the other one is off. So because we have like 2 amp running here, like 50% of the time we have 2 amp running here, but which is on average 1 amp. That's why we have 1 amp there. Oh, we need a capacitor here to even it out, otherwise. This is the circuit of the inductive balancers. Basically, this one inductor two switch kind of thing is kind of like a buck or a boost converter. And then, well, I can go in more detail, but we don't have time for that. And then here's the normal, you still have the normal MPPT. Then you also have capacitor balancers. Let's see, how do I explain that? I feel like what I'm drawing already doesn't make sense to most people, but let's go. Like the capacitive ones are, well, how do they do it? So basically, you're trying to get like the voltage, you try to keep it the same. And basically, like once the diode goes in conduction or something, like the voltages are not the same anymore. So, but as long as you force the voltages to be the same, you will balance your system and you will make sure both of them are balanced. How do they work? They have a capacitor. Let's see. And then they make sure the voltage of the capacitor is V MPPT. And then they have a bunch of switches. Let's see. How are we gonna do this? They have one switch here that can go in two positions. My desk is falling apart. Let's see. So this is a two-position switch. That's, I don't think it makes much. Like I need a trackpad or something that's a little bit better than the MacBook one. Let's see, one switch there. There's probably easier ways to connect this, but the idea is there's a two-position switch here and a two-position switch there. And now when like the two position, let's just number. So like there's like, this is switch A, this is switch B. This is position 1. This is position 2. And what it does, it puts the capacitor in parallel. So it puts the switch in position 1, then the capacitor like is connected in parallel with the top cell. So the voltage on the capacitor is equal to the voltage on the top cell. Then the switch goes to position 2, both of them. So then the plus and minus of the capacitor gets connected about like across the bottom solar cell. And then by switching really fast between position 1, position 2, position 1, position 2, you make sure that like the both solar cells voltages are equal to the capacitor voltages, and because of that, the solar cell voltages become equal to each other, and because the maximum power point voltages are the same, this works. And then on average, you will get your 2 amp here. And you could probably have like capacitors here as well that are a little bit smaller than the big one. So this is the big one. But in practice, you don't really need that because your solar cells also have internal capacitances. Well, depends how fast you switch. But let's see. Yeah. This is kind of like how the capacitor balances work. The benefit or the inductive balancer with respect to the capacitive balancer is that with the inductive balancer you can configure the voltage on the top and the bottom cell to be different. So if their maximum power point voltage is not the same, like unlike this example, you can still make it work with the inductive balancer. You wouldn't be able to make it work with the capacitive balancer. This only really works when the maximum power point voltages are exactly the same. So that's the MPPT, like 2 different options, and like pretty much like all the papers are like, well, are like more complicated versions of what I just showed. I want to go back to the MPPT graph for a bit. So here, like you see that the maximum power point voltages are the same. They're not really dependent on irradiance. So capacitive balancers could work, but they are dependent on like temperature, for example, and also on how many cells you put in series. So like if some section of the array is, I got a message, is warmer than the other one, like capacitive balancer already doesn't work as well. How do I keep the PV from frying the MPPTs if the battery disconnects due to BPS? Just let me read again. How do I keep the PV from frying the MPPT if the battery disconnects? What is BPS? Like, I don't understand the question. I don't know what BPS means. Oh, BMS. BP, battery management system protection system. So what is the, how do I keep the PV from frying the MPPT if the battery disconnects? So what are you doing? You're disconnecting the battery from the MPPT output, and then the MPPT fries? Like, just buy an MPPT that doesn't fry itself, because really, like, or I'm not understanding your question well. Like, why does your MPPT fry? Wait, Dan, can you just put your microphone on? Does it work?
Can you hear me now?
Yes, I can hear you.
Okay,
What, can you-
so I'm bringing up a common problem that teams have with, say that they're charging off their array and their batteries reach an overcharge state, and their battery management system disconnects the battery, so you no longer have a active load against your MPPTs. Can you just describe what teams should be looking for or testing for in order to make sure that their system is robust to this condition for solar cars?
I think you got, I think I got your question. Let me just see if but now my Jamboard is not working anymore. My computer stopped working.
Elmar, this is Alan. Do you mind if I say something? Elmar, can you hear me?
I think he got disconnected.
Oh, okay.
I think you have the floor, Alan.
Well, I was going to basically try to maybe just come at it at a different angle, Dan. I know what you're asking, because there are some MPPTs that, you know, the hookup sequence, if you will, is generally, you know, hook up the load first, and in this case, it would be batteries, and then hook up the array. And so it would seem that the reverse is true, in the sense that if you want to disconnect the system, you would disconnect the array first and then disconnect the batteries. But if that is true, then it sounds like that particular MPPT would be sensitive to frying, as you say, should a BPS system disconnect the battery before the array is disconnected. Is that a correct interpretation?
Yeah. There's conditions where if you get your connection scheme incorrect, you'll put a over voltage on your MPPT.
Right. Okay. So yeah, I'm not sure if Elmar.
Yeah, I'm back. Like now I had a battery failure, but I'm back.
Okay. So did you understand, Elmar?
Like, I missed a lot because my computer stopped working.
Okay. So I'll try to put it simply. I think what Dan was getting at is some MPPTs may be susceptible to being damaged if the battery or the load side is disconnected.
Yeah. So that it's just like, so you have like boost MPPTs, right? And then they like, so they, can I just make a drawing again on the whiteboard? Let's see, can I share my screen again? Like, it's a bit messy now, but I'll get to it. Do you see a Jamboard now?
Yes.
Let me just, and it works again. Yes, here. So you have a boost MPPT. Let's see, can I just? You have your PV. Wait, I'm a little bit out of. You have your PV. You have your like boost convert. Wait, I was able to do this a little bit better. You have your boost converter. And then you have your diode here. And you have your capacitor here. And then like you connect your battery, right? And then the battery management system, like has like a switch that disconnects the battery from the MPPT once it's fully charged.
Well, you wouldn't want that, but if you reach an overcharge state because you didn't set up your power tracker to the right charge termination, that could occur.
Yeah, so ideally you would just turn off your MPPT before this happens. Let's see. Ideally, you would have like some kind of like enable like line on your MPPT that would be controlled and like before that switch gets turned off, right? But like, well, let's say that doesn't happen, yeah. And let's say like the MPPT has some way to limit its voltage as well to the maximum power punch, to the maximum battery voltage, but that doesn't work either. And then, well, yeah, and then your battery turns off this switch. And then you see that you say that teams are like frying their MPPTs because they disconnect them from the battery, pretty much, or because the battery disconnects them from the battery themselves.
We've seen that problem before.
What MPPTs have you seen this?
I want to say the AERLs, those were a buck type, and I think the problem was the capacitance or the capacitor on this on that board would go because it wouldn't correct fast enough to the to the over voltage that because if you lose the full volt output. Now that might have also been just because the inverse of that is when you reconnect that, you're going to have an inrush go back into that final stage. So it could have been either or, that you had a breakdown of that capacitor in the fault, or as a subsequent turning back on.
There's lots of different things that can happen. Let's see, like to me, it already sounds like the MPPT is not protecting itself. Like it just sounds like the MPPT is creating an overvoltage on itself and breaks itself. Like there's not really much you can do about that, other than like talking with your MPPT vendor to like get that fixed. But what also happens, like, there's so many things that can go wrong. Like I'm just like trying to see what useful things I can say about this.
I was just wondering if you had any advice for teams when they're selecting, different MPPTs, because most of the time they're made for fixed, installations, not an active, solar car type solution where you're going to have more chances of, disconnections, open circuits, broken array connections, those type of things. If you could point out what should they be looking for when they're either buying or producing their own.
Shoot. So like I can, there's something I can like that I'm familiar with is that like what I've been seeing with teams that I've been dealing with is that they don't understand one of the specs of the MPPT very well, and that's let me just go to a data sheet. In the data sheet there I have this number here. can you see? So there's array voltage, array current, output voltage, which should be like the maximum should be like matched with your maximum battery voltage. But there's also like this other one, like output shutdown voltage spike. Like usually MPPTs have some kind of protection built in that let's see. When you disconnect your battery from the output of the MPPT while it's in operation, you can expect the voltage to rise above the max limit. But usually there's some protection built in at some voltage that it can like because that it can literally not cross because of the protection. And for my MPPTs, that's usually configured to 175 volt. What like, and the reason I did this is because like the Wave Sculpture 22 motor controllers are also like rated from that maximum voltage. So like what some teams do is they connect their motor controller and MPPT in parallel, and then they connect that in parallel with a battery, and then they disconnect the battery from the system, which makes that your MPPT and your motor controller are connected together. And you should make sure that this maximum output spike from the MPPTs is compatible with your motor controller and anything else you put on your DC bus. But that's the one thing I can come up with. So for example, with the DriveTech MPPTs, the max output voltage spike on the output is like 230 volt or something like that, which is higher than what the Wave Sculpture 22s are rated for. So what I used to see a lot of teams doing is disconnect their battery and then their MPPTs give a spike, and then that would blow up their motor controller, making a short circuit on their bus, therefore also blowing up the MPPTs, and then literally their entire system would be fried after disconnecting the battery.
Elmar, there's a question in the chat.
Okay, I don't see it, but I look at it now.
From
how much time do we have? We have a question about the MPPT algorithm.
Yes.
Can we just move
Hello.
on to that?
Sorry.
Yeah.
Yeah. So we have a question about the MPPT algorithm. What we can't we've been trying to, but we can't wrap our hands around how the PWM duty cycle choice is taking place while at the same time you're trying to optimize for both the IV curve and your output voltage based on the battery voltage and your boost converter.
So usually you only care about the input voltage and input current because the output voltage is pretty much defined by the battery, right? And usually you want to like put all the power you have in the battery. So let's see. What did you say? You have a duty cycle? Yes. So your duty cycle on the switch in your MPPT, your PWM duty cycle, pretty much defines the ratio between input and output voltage of your MPPT. And usually your output voltage is pretty fixed because the battery voltage doesn't change rapidly. And therefore, by changing the duty cycle, you can change the ratio between input and output voltage. And because the output voltage is kind of fixed, you can therefore choose the input voltage by selecting a circuit and duty cycle. Does that make sense so far?
I think so. Yes. Thank you.
And then, well, you can select your input voltage by setting a certain PWM duty cycle. And then you can sweep that input voltage to get a little like IV curve graph. And then you just read that graph to see where the power is highest, and then you see what voltage corresponds to that, and you try to stay on that voltage. I think I went a little bit quick, but hopefully that helps a little bit.
It already helps. Thanks a lot, Elmar.
Yeah, you're welcome. If you want to do like a one-on-one and go in more detail, we can do that.
Thank you.
You're welcome. Are there more questions? Like how much time do we have left? Does anybody know?
Well, you're over the hour, but I believe that we're allowed some extra time if we want.
When is the next meeting? Let me just double check before
Next meeting's
Next
don't
one
start
is-
till 3:15.
half an hour from now. Okay, well, let's do like 15 more minutes then for questions, right? And then we have 15-minute break. I feel like, are there more questions?
we have one more question if no one has.
Yeah, go ahead.
So I would be curious to hear your opinion about how to increase the efficiency when you have lower currents flowing from your solar modules. So something I noticed when looking at MPPT graphs is that usually the efficiency graphs, that is, you usually have a lower efficiency when you have a lower current, but there
Like this?
are some, yeah, like that, yeah. But there are also some variations that allow you to keep almost like a steady efficiency through a larger range of input current, right? So I was wondering if you could go into the differences between those two types of MPPTs.
Like this. Like,
Yes, yes.
yeah, let's see. Yeah, like the reason. Well, yeah, you just like it's really it's really complicated. Let's see. Like the reason for this being more efficient at lower currents is because of lower core loss in the inductor and lower switching loss in the switches. Let's see. But I'm not gonna like do explanations about inductors and switches. Well, I can do the switches. That one is something I can do. So usually you have like a converter with like an inductor. Let's see. And then you have like two switches. Or like a switch in a diode, but like then the diode, you could also use a switch for that you like turn on and off in a smart way so it acts like a diode. And then usually you have some capacitance like, well, there's multiple factors that contribute to switching loss, but let's just keep it simple. Let's say there's like little capacitors like in parallel to the switches on the MPPT. So this is like the input of the MPPT, where you connect your PV. This is like the output. And what happens is like every time you turn on a switch, you short this capacitor, and therefore you lose all the energy in the capacitor. And therefore you get some standby power consumption, and therefore you get like, well, yeah, you get this, right? You get this standby power consumption of like 1.5 watts. That's mostly because like 1 watt of that 1.5 is because you're just shorting the you're shorting the capacitors in parallel with the switches that are parasitic, so you cannot really get rid of those capacitors. So what I do on my MPPT is I have an extra inductor with an extra switch, but this switch is a little bit smaller, and therefore its capacitor is also a little bit smaller, like 10 times smaller. And what I do is step 1 is turning on this one. So let's say the current was flowing like this, and the voltage here was equal to the output voltage. So let's say like this switch was closed. What I do is I turn on this switch, like where I set the number 1. It's close, this one. Then current starts running here because there's a voltage here. And because you set a voltage equals an inductor, the current starts rising. And then at some point, this current here becomes higher than the current there. And then at some point, you start discharging this capacitor. And you basically transfer the energy from the capacitor into the extra inductor L2. And then at some point, because you're discharging this capacitor, like the voltage stops dropping to 0 without wasting the energy in that capacitor. And then once that voltage here drops to 0, I close this switch. Wait. One sec. First I close switch 1. Then then the current here becomes higher than the current through the main inductor, L1. Then I open switch 2. So, and then the current starts discharging the bottom capacitor and charging the top capacitor. And then once this voltage is dropped to 0, I close switch 3. That's the trick I'm doing. It's complicated. And then all this energy that got released out of this bottom capacitor is stored in L2. And in order to release that, we need another diode here. And then we transfer like the energy that so basically we try to move the energy from this capacitor that's parasitic to an extra inductor. So like we move energy from this capacitor to that inductor, then we turn on the switch, and then we move the energy from that inductor to the output again, to like this capacitor here. Like I'm not sure if this makes any sense at all, but this is one way to get like less switching loss and therefore higher efficiency at low currents.
That does. Thank you. Thank you for the explanation, Elmar. That is helpful for understanding
Is
the
it?
difference in the
Like
curves.
if
Yeah.
you want to learn more about this, there's papers on this. Like they're like 30 years old, and everybody has pretty much forgotten about it. Like they're from Virginia Tech. Like I can forward the PDFs if you send me an email.
That would be great. Yeah, I'll be doing that. Yeah. Can I contact you via Discord? Would that be okay?
Yes. What also works is email.
Okay.
My email is hello@elmar.solar.
Awesome. We'll be sending you an email. Thank you, Elmar.
Like it's right. Or sometimes I'm also not very responsive on email. Like LinkedIn works as well. Like you feel free to try all the options that are on this sheet. Like email should work, but let's see. There's more tricks, but like, yeah, 0-volt switching is one of them. The other thing is you can just PWM your PWMing. Like you can do like normally like you PWM your thing like to get like a certain current. What you can do is you can do something like this. You PWM for a bit, then you do nothing for a bit, then you PWM for a bit. And then like your current graph starts looking like something like that. And because now you're only PWMing like half of the time, like you have half of the switching loss. Like, well, it's a little bit scrappy how I drew it, but I'm not even sure how this is called, but the downside is that you need like bigger capacitors if you want to keeping your voltage on the input steady, right? Because you get graphs like this, and the ripple on the graph is going to be higher than the ripple that you would normally have. Or you need to switch faster. Well, there's so many. It gets very complicated very quickly, but there's lots of tricks and smart ideas and things you can do that pretty much a lot of people are not doing because it's too complicated. But really, once you got it working, it works, right? Like it's not like it's complicated to produce. Like it's just complicated to make the algorithm initially. I don't really see why those big Chinese converters are not doing it, because they make millions of them and they are so fucking huge. Like they could make those things like 3 times smaller. And yeah, but working together with smart ideas and big factories, like it's not really working out usually. There's one more trick I wanted to explain to get more power out of a shaded array. We have like 7 more minutes, right? Can I do that? I'm just gonna do it. So let's say you have 1 solar array or let's do 3. Let's be crazy. Let's do 3 solar arrays this time. So what I think teams should be doing, because what we've seen so far is that like the series boost MPPTs don't really work well. And then the buck boost MPPTs do work well, but their efficiency is low because you have like 4 switches for every MPPT. Like what I think and they're all active all at once as well. What I think we should be doing is, but like, what I think we should be doing, like MPPT, this is a boost. That connects to your battery. So we all saw this picture with this diode here, right? And then here was the cloud. And the other one had like sun. And what we're basically doing, because this one has only 1 amp, and the other one might be having like 3 amp. And we all know that like if you run the numbers, it works out to like to run your current like this. And then like your voltage here becomes like 0 volt or even negative. But what I think we should be doing is, let's say they're all 30 volts. I think because the power here is like 3 times as low. And the current is the same everywhere because we like to connect everything in series. Like I think the voltage should drop rather than that the current should drop. Like we should like for the shadowed one that gets 3 times less power, I think we should be getting 3 amp 10 volts. But that's not how IV curves of solar cells work. Like unfortunately, like we would like the voltage to drop rather than the current, but it does not, because that's not how solar cells work. But I feel like there are ways to go from this to that, because basically we want to like triple the current and like decrease the voltage by 3. Like, well, that's a perfect application for a buck converter. So what I think what we should be doing instead of this diode thing, maybe I should make a screenshot of this before messing it up. Yeah, I think what we should be doing instead of this diode thing, we should get rid of that, and we should just connect a buck converter. Let's see. Let's see here. A buck converter is not that difficult. Well, in my world at least. But like, well, it needs a capacitor as well. But maybe you can use the one of the solar cell. Here we need a buck converter. And then that one is already connected, and then we connect this there. Yeah, done. And we just run it at a duty cycle of like, what is it, like 33%, I think. And then we just make sure that the inductor current is 3 amp. And then because the switch is only on 33% of the time, this is 1 amp. And then because the diode is like on like 66% of the time, this is like 2 amp on average. Like it all works out. Like if you run the numbers, this all works out and you get like all the power from your array. And like this wins you like 30 watts when there's shade. Because otherwise it would be like 0 volt and 0 watts on the middle one, and now you get 30 watts. I think that was a smart thing to do. And then once the sun comes back, let me just make a screenshot again. When the sun comes back, well, that's too difficult. When the sun comes back, like we just turn the switch on, and then you just like you have some extra resistance of this switch and this inductor, but shouldn't be very significant compared to the 30 watt that you win when you do win. That's it. I think we're out of time now. We have time for one more question, I think.
So Elmar, if you don't mind, so in summary with what you've just shown there, you're basically saying that instead of a bypass diode, even an ideal bypass diode, you would suggest possibly looking into a boost,
Buck,
boost converter on a group of cells.
a buck, basically what I'm drawing, like the extra thing I'm drawing here is a buck converter.
Yeah, sorry, a buck converter from 30 volt nominally to 10 volt. Got it. Okay.
Like, let's call it like a buck optimizer or something, like a solar optimizer. Like they already exist, right? But not for like solar car.
Right. Okay. I get it. Thank you.
Yeah, because like, yeah, I think it makes sense. And then rather than 0 volts, like, well, with a normal diode, you have, with a normal diode, you have like a negative voltage. With a perfect diode, you have like 0 volt. And then with this buck converter, you actually get some useful voltage where you can actually get some positive power out. Yeah.
Right.
Like the only downside is that once you only turn this on when there's shade, and when there's no shade, you just leave the switch of the buck converter on. And then you do have some extra resistance in your string, but it's not much if you design it well.
Wow.
Could be a couple of milliohm, like. But like, someone should make this. Yeah.
I know someone who should make it.
Yeah, are you like telling me to make it? Like,
Well, his initials are EP.
to be honest, like it's like I already did some simulations and selected some parts, and like it's not shouldn't be difficult to make. I just there's so many projects I have in mind that could potentially be way more important than this. But yeah. Like I know people that already made this, to be honest. There's 2 companies in the Netherlands. One of them is Taylor Solar, and the other one is DC Opportunities. Like maybe I should just like make them sell their stuff to Solar Car.
Well, what level are they? Are they doing it at the cell level, or are they doing it at like a substring level? Or
They did like they connected like 5 or 6 cells or something per book.
Okay, that's interesting.
Like they do like they have like these solar arrays, and they kept like 1 string on the length or the vertical. Like I don't know what they do. I think no, they do 6 or 4. Like they make like a little cluster. And Taylor Solar, they're doing it on actual residential solar arrays, and they are just replacing this diode box on a solar array with like 3 or 4 diodes for like 3 or 4 buck converters. And they are doing this to like increase the lifetime of the solar arrays and to reduce the heat hotspots in the diode box.
So if I'm not mistaken, they're probably marketing these ideas as shade tolerant solar panels, right?
Well, like Taylor Solar is also just doing residential stuff, right? Or industry stuff. Also, like they're doing it because if like a bird puts poo-poo in your solar array, like they don't want your lifetime of your solar array to degrade. And DC Opportunities, they're doing it for sailing boats. They have like shade from their sails.
Right.
And they're selling it to like rich Swiss people with sailing boats. Like,
Right.
They're gonna open source their design. Like they made a deal with those rich sailing boat people because they felt bad because they're buying all those expensive boats and doing bad shit for the environment. Like they made a deal that they open source the design. Like to greenwash their like sailing boat hobby. Like I thought it was funny, like
Yeah.
but like they say they open source it, but then they only open source it once it's done, and it's never done. Like even though their system is working, they haven't open sourced it yet. Like
Yeah.
it's like fake open source. Like now we want to publish a paper first, and we don't want to open source it before we publish the paper because it would like take away the novelty of the paper. I'm like, yeah. And like next week you want to do a patent, and then in 1 year you're competing with Tesla instead of like open sourcing your patent. Well, Tesla also open sourced their patents, right? But and I feel like they have lots of strings attached to that.
Interesting.
Anyway, like I feel like I'm like, should I just make one? Like it's almost easy. Like let me just ask those guys from DC Opportunities if they've open sourced it yet. Like they showed me a demo, like it really worked. They showed me like graphs with power without and with the system, and it was super significant. So imagine it will be super, I know it will be super significant for canopy shadows as well. You got like an extra 30 bucks or something like.
What were the two companies' names?
Taylor Solar, put them in the chat. Just you can say. I'm not sure how to type in the chat. I am Taylor Solar, and then the city is Eindhoven, and then you had DC opportunities in Delft, and you had and then I should make one too, right? Like,
Okay.
because I'm sure theirs is not optimized for solar car. Like, I should probably cooperate with Taylor to make one for solar car. I don't have to do the entire thing all over again. But cooperating is so difficult with companies, right? Like you get these egos from different companies and money and like, and then, oh, now we have a patent. Oh. Oh no, you cannot do that. Like our lawyer is coming to you.
Right.
Like, oh no, we're not going to tell you about our technology anymore because someone offered us money. Like, honestly, like I should probably do this. Like, does someone want to do beta? Like,
I'm always game to try to experiment with obviously my solar panels and such.
you wanted to do either IV curve tracing with the MPPT that I made, right? Which I
Well,
support-
yeah, I mean that's one
which
thing
I
that I'd like.
support nowadays.
But I think now that you bring up this idea of a bucking converter, I think that would have a greater impact on solar cars than a IV curve tracer. But both are
Well,
useful.
you should first trace your IV curve, then become aware of the energy you're losing, and then fix the
Sure.
energy you're losing.
Sure.
Like, you're not really like becoming aware of the problem and just attaching like 3 voltage measurements to your array, so to see when diodes go in conduction and what the voltages are on your cells and how much lower they are than you would ideally hope them to be, is like the first step towards optimizing your system, right?
Right.
Like, but then teams are always like, oh, we're just like consuming extra energy and adding extra weight by connecting this fancy monitoring system. But really, that's step 1 to like winning a lot. Like, first you lose a little bit by making a good data acquisition system. Like, it costs a lot of time and a little bit of energy and weight, and then you realize that you might be able to like win 100 watts somewhere or something.
Right.
Like, you should measure what's going on first. What I think you should do, Alan, is like IV trace curve individual cells instead of like entire strings.
You mean on a finished car, on a finished
Yes.
array?
Yes, like just during testing and operation. Yes. Like,
Well,
the teams should just do it themselves. Like, they should just monitor like every single cell. Just like
that's
they
a
do with
lot
the
of
battery,
wiring.
right?
That's a lot of wiring.
Well, you can make groups of like 6 cells or something.
Yeah, that's what I'm getting at. I think it's useful to get IV curves for relatively small groups, say the panel level, and
You have like
and again,
260 cells or something like that, right?
yeah, about 260 of the E60 cells for a 4 square meter array. Yes.
And if you divide it by 6, you get 43. I think you should measure at least 43 voltages.
Oh, sure. Yeah, I mean that's perfect. That wouldn't be a problem. Well, that would be relatively easy to implement.
So you have these
And then,
boards that
but
can
the
measure
important thing,
16 voltages.
but the important thing though is once you have the IV curves of these groups of cells, you have to know how to interpret it.
Yeah. Yeah, like you need to know what you're doing. Yeah.
Yeah, it's interpreting the curve that then tells you what you need to do, and it may mean you have to replace the module, obviously.
You have to replace what? I cannot hear you anymore.
Can you hear me now?
Yes.
With the interpretation of the IV curve of a module, let's say, it may mean you have to replace it.
Replace a module?
Yeah, because it may be irreparable.
It might be broken, you mean? Or?
Exactly.
Yeah, so that's something you can learn with this.
Sure.
Like if you have damage on your way, and then you need to like, well, yeah. Or you can bypass a single broken cell or something to make the problem a little bit less worse. Like
Yes,
Or-
those are all things that we have done with teams in the past on a race, where we would help them diagnose a problem. And from that, some quick fix was made during the day, let's say, and then at night they replaced the module.
I remember doing surgery on solar arrays like in the middle of the
Yeah.
desert.
Yes.
Like at 3 a.m. Like and then yeah. And having like 1,000 of insects like going between the array and your carbon, like like then feel free to like stay in touch. Like I should well yeah. People should just email me if they want to stay in touch because I'm not gonna keep track on all the people that join.
No, they'll contact you, Elmar. Trust me.
Would I be able to get this presentation I joined late? What do you want? Like just slides? They're not going to be super useful.
I'm sorry.
We can do a one-on-one. We can do a one-on-one. Email me. Just email me. We can do a one-on-one. I can give you a private presentation.
Well, Elmar, you're aware that this entire presentation is being recorded.
Yeah, like I
And-
said it last time as well, but then I wasn't able to find the recording.
Last time what?
Like 2 years ago.
Oh, well, no, this year's different.
Okay, like I should be able to look for those things. Also,
Well,
I found like a buck converter that goes from 48 volt to 0.6.
Wow.
So it was like if you do that the other way around, you can just like boost like one solar cell to 48 volts.
Now that would be wonderful.
But like it's made for like server power supplies. And like it can output like 0.6 volt 300 amp. So you can just put all your solar cells in parallel and connect them to this.
Right.
It's only like 96% efficient, I think. Well, just something to think about.
Yes.
Like, it's like there's so many things you can do with solar arrays. Like I feel like only the Japanese teams are really like putting some effort in it.
Well, how effective was your Sabine system?
Like, well, sometimes we had like plus 30 watts, but not all the time. It was mostly like effective for the shade. Like we couldn't really measure a noticeable difference for the curvature differences. Probably because the system was not working well enough, not because there was nothing to win. But usually, but for the shade, we would usually win like 30 watts when there was any shade at all.
I see.
And that's really worthwhile. Like that's the first thing you should focus on, getting rid of the shade inefficiencies. I'll ask for the recording as well. Yeah, I'm wondering where you can find those recordings as well.
I can show you. It's not hard. I think if you go to the,
With new presentation starting is in like 3 minutes, right?
I'm sorry.
There's new presentation starting like in 2 minutes.
Yeah, I believe so. But I can show you